Good morning, Samay.
Good morning. Good morning, sir.
Good morning.
Good morning, sir.
Yeah,
Good morning, Pankaj.
Pankaj.
Good morning, sir.
Pankaj.
So, participants are joining, so we will start within 2-3 minutes, sir.
Fine. Okay. Yeah, Dr. Pankaj, just I want to share my screen, whether it is moving or not, just I have to check up.
Okay, sir, you can share, just we have make you as co-host.
Yeah. Yeah, my screen is visible.
Yes, sir.
Also sliding.
Yes, sir. Sliding, moving, sir.
Sometime it is not sliding. That's why
Okay,
I want
sir.
to check before
Yes, sir. Yes, sir.
starting
Yes,
of the program.
Yes, sir.
Now it's okay.
Okay, sir.
Now I am in number 13 slide.
Okay, sir.
Okay, no?
Prakash, sir will start.
Yes, sir. Sure. Sir, your slide is properly visible and your voice is also audible.
Yeah.
So,
Fine.
and right now you are on slide number 13.
Yeah.
Okay. Good morning, sir.
Good morning.
Good morning, one and all. Present in this final day of our faculty development program on 3D printing and design for academicians and entrepreneurs. So this session, the resource person is Dr. A. Kumar, and his topic of deliberation is defense applications in additive manufacturing. So for audience, let me introduce the speaker. Professor A. Kumar is a professor and head of the Department of Mechanical Engineering at NIT Warangal. He has completed his doctorate in mechanical from Osmania University. His specialization includes friction stir welding and processing, additive manufacturing, electrical discharge machining of titaniums and superalloys, fabrication and characterization of micro and nano composites. He has supervised 10 PhD students and 30 ME theses and currently supervising 8 PhD students. He has published more than 100 research articles in reputed national and international journals. He has also completed many sponsored and consultancy projects from ARDB, DRDL, and other central government funding agencies. He has delivered expert talk in various short-term courses, faculty development programs, seminars, workshops, and advanced topic of manufacturing technology. He is also a lifetime member of several professional bodies. So we welcome you, sir. Now I would like to hand over the session to you. Sir, please.
Yeah, thank you. Uh, shall I start?
Yes, sir.
Then,
Yes, sir.
okay. Yeah, good morning, all of you. Thank you very much for giving me the opportunity to share my knowledge in Atal FDP programming on 3D printing process. And also I thank to the uh, coordinators, Dr. Pankaj and other uh, faculty members and head of the department, Dr. P. Sammaya and other faculty members. Good morning to you all. Well, so without late, I can start my presentation on additive manufacturing, especially defense applications of the components produced by additive manufacturing process. So, so what are the difficulties that are come across during printing of these materials with respect to the metallurgical, mechanical, and geometrical features and other functional aspects we are going to discuss coming forthcoming slides. Uh, so basically, we are working on metal additive manufacturing. We are not worked on polymer-based additive manufacturing process. Basically, before going to enter into this area, I worked in welding for aluminum alloys, especially TIG welding and friction stir welding. Then, so because of the latest area, I move on to this area like additive manufacturing process. Already the most of the resource persons given you outline of the additive manufacturing process and different additive manufacturing process and even then my presentation is different, not completely different. It may be some slides may be similar to the previous resource person. We don't know because this topic is given to me additive manufacturing with respect to defense applications. So today I'm going to mostly talking on metal additive manufacturing with respect to defense applications. So the my focus is on especially solid-based additive manufacturing process because our students, especially in NIT Warangal and other students other than institute, because we are running PhD programs also part-time basis. So our students also may be there in other than NIT Warangal. So they are working on under my guidance mostly on friction stir based additive manufacturing and additive friction deposition and wire arc additive manufacturing process. These three areas we are working since 2000 onwards. Okay. The basically additive manufacturing process. How do you define the additive manufacturing process? How this additive manufacturing is different from other manufacturing process like especially welding. Then coming to in welding also we have solid state welding and fusion based welding or liquid based welding process. The same principle we can apply here additive manufacturing process so that you can able to generate the component without much any difficulty. So in my opinion, additive manufacturing process is not a new area. So it is old area like forge welding. Have you heard of forge welding when we are studied in undergraduate program? The concept of forge welding we are still utilizing for advanced welding process. Similarly, welding process can be used or can be integrated with your computer and XY platter. That means CAD CAM to interface with your welding power source. It becomes a additive manufacturing facility that we can call it as people are talking about wire arc additive manufacturing process. So if you remove the robot and other computer-based tools to the wire arc additive manufacturing facility, then it becomes a simple arc welding machine. So this also we are going to discuss in today's class if time permits. Uh, then I'll go with the introduction. Before going to the introduction product, so basically, what are the different manufacturing process? How you are differentiate one process to the other process? How do you make a component with the use of either combination of two or more process or alone can be used to make a product? For example, this component I'm going to generate any process. I have three processes are available. Then, depending upon our convenience and availability, we can choose any one of the process to get your final object. So this is my final object using a subtractive process. That is removal of material from the stock using any conventional or unconventional machining process that enables to give your product dimensions. So that is comes under subtractive process. So in subtractive process, the volume of the material does not same before and after the process. So after the process, the volume of the material is reduced compared to the before the process. Whereas coming to the formative process, I can take any forming process with the help of die. Then I can push the material through a die so that I can get this shape. So what is the observation between subtractive and formative process? So we are not going to remove any material or addition of material. Only you are going to change the shape one form to the other form. So that is known as a formative process. That is, there is no addition of material after the process or removal of the material. So neither removal nor addition. So the volume should be constant in a formative process, only change in the dimensions before and after the formative process. Then coming to our actual topic, additive manufacturing. Why don't we generate this component through additive manufacturing facility? Yes, it is possible. So what I do is I can deposit a layer by layer according to our predefined geometry, which is uh, developed through CAD environment. Then based on the CAD environment, then you need to generate the component by melting the your powder particles or uh, wire, sometimes supplied wire, or combination of these two also there in the latest technology, or otherwise you can add even solid material one over the other so that it becomes a your required geometry. So it looks like a pack of cards. So in the pack of cards, you have 52 cards. So one by one, you can add it to that so that it becomes a 3D object. So in the same way, we are going to generate component through additive manufacturing process. So in this, the addition of material takes place after the additive process. So initial volume is not equal to the final volume of the component in case of additive manufacturing process. So introduction to additive manufacturing is a manufacturing process in which functional parts can be made by adding materials without using special tools, jigs and fixtures. This is very important information with respect to additive manufacturing process. So here we don't want required any additional kind of material tools that are useful for developing the components. For example, if you take subtractive process, suppose I'm using a drilling process. For guiding the tool, you need a fixture and jig and fixture is required to hold the component as well as guiding the tool. So these additional tools added to the cost of the product when you are giving a total cost of the price of the product. So that's why the additional tooling is essential in case of subtractive process, sometimes formative process also. Whereas in additive manufacturing process, there is no requirement of additional of any uh, feature, any tools that are used for making the components. So in that case, the cost of the component you are going to generate through additive manufacturing process. So with respect to the, I'm talking about additional tools, the reduce the cost. So what is the advantage to do not have an additional feature, additional tools like tooling, jigs and fixtures? You can save a lot of time. So as you know, you can see the manufacturing process. So the 5% is time is required to complete the job. The remaining 95% of the time related to your fixing of the component during the process. So the 94% of the time is utilized to bringing another features of the product in case of additive manufacturing process. So that's why you can have a less wastage, lead time also less, and the cost also reduced. Then with respect to the independent of complexity, so so the component is more complex nature. Then you need to go for 5-axis vertical milling machine or 6-axis. Sometimes you can go for 8-axis milling machine. So additional access added to the existing machine, the cost of the machine is going to increase. So depending upon the complexity, you need to have different access. Whereas in additive manufacturing, there is no need of any uh, additional tooling or additional access to develop the component. So the basically there are 8 steps involved in any additive manufacturing process with respect to non-based additive manufacturing or beam-based additive manufacturing process. So the beam-based additive manufacturing process, you can use either electron beam or laser beam to melt your raw material. Raw material may be in the form of a wire or powder form. Whereas non-beam based material, you are not melting the your powder or filler wire. Just you can add sufficient amount of energy. That energy is utilized to softening the material. Then you can apply the force according to the applied force. The bond is created between the two sheets that we are going to discuss in the forthcoming slides. The first most important step in additive manufacturing process is a CAD file. So you have certain designs, or you can create your own designs that not depend on any other designs which are already there in the literature, not required. So based on your thinking, based on your ideas, that is own thinking, critical thinking, leads to development of a new solutions. So that solution can be converted into your CAD model. So once you convert the CAD model in the CAD environment, that can be converted into again STL file. So STL stereolithography file is a 2D geometry file. So whatever the 3D object which is generated in the CAD file, convert into slices. So each slice is a 2D object. So strictly speaking, it is 3D, but the thickness of the slice is very, very small compared to other dimensions. So that's why we can call it as 2D, like thin sheets, plates. As a plate is a 2D object, we can say, because the thickness of the plate is very, very small compared to length and width of the plate. But in microscopic view, plate is also considered to be a 3D object. So even the thickness is very small that microscopically we can call it as 2D, 3D, sorry. So similarly, the 2D file, the STL file, the combination of all triangular files, which leads to a 2D object with the minimal thickness. So each layer has its own geometry or same geometry or different geometry. It doesn't matter. So irrespective of any geometry on each layer, so the machine will can understand by the STL file. Now the next step is the file is transferred to machine. So because the STL file is a combination of 2D geometry, so this file can be understood by the machine. So then you can set up the parameters according to your requirement. Somebody wishes to work on polymers, somebody is titanium alloys, aluminum based alloys. So there are different parameters for melting of these different materials. You need to fix the what are the parameters that are required to develop the component without much any defects. So once you set up the machine parameter, you can build the component using the additive manufacturing equipment. Then after building, you can remove the component from the substrate. Then you can go for post-processing, then applications. So what I am trying to say is the developed model is an important step, and this model is converted to STL file, then transferred to AM machine, and also you can set up the parameters, then you can build the component as per the 2D geometry. So once you are completed your job, then you can remove the component from the substrate and you can use for any applications. Now coming to this slide is very important for you to understand where AM can be used, where CNC can be used. So as a layman, I simply cannot choose CNC or AM process because we are engineers. We are working for the product development. We are also looking for the minimization of cost to produce those components, and it is affordable to the customer and leads to increase the GDP, etc. So for example, I'm taking with respect to the material, I have different kind of materials to generate this component, for example. So this is a cup is made up of ceramic material which can hold hot fluid. So my objective is uh, holding of hot fluids. So for that, you need to select a material. Suppose if I select aluminium or copper, what is the problem? If you are keeping the hot fluid in the copper and aluminum having very good conductivity, the heat is transferred to the person who are having the cup in his hand. So it is not advisable. So what is the criteria for the material which is in hot condition should have low thermal conductivity. So which then you can select the material which is reference to the low thermal conductivity materials. So in that case, ceramic is the best material to choose uh, holding a hot fluid in a cup. Then this is after my objective, then I have chosen ceramic material as a work material. Then I have two different process, CNC as well as additive manufacturing process. Then which one you are going to select? Suppose I don't have an idea much on additive manufacturing process. Simply I can go straight away CNC machine. Okay. So once you are selecting a CNC machine, so your work material ceramic material is very hard material, and you can choose the cutting material should be much higher hardness than ceramic material. So that is one important criteria. Okay, you can select, let us say, diamond as a cutting tool material. Now you can go for machining. So which type of machine is required to generate this component? Yeah. So definitely you can go for a 6-axis vertical milling machine. Okay, I can provide all the accessories to generate this component. Then after fixing the component, you are going to machine this component using 6-axis vertical milling machine. Then while machining, what we observed is there is irregularities much more. The surface finish which you are getting through milling process is not equal to your requirement. Then I can realize that, oh, this process not suitable for ceramic materials because ceramic material is very hard material, comes under brittle category. So even if you remove the material is removal material is not a continuous form. It is a discontinuous nature. So that's why you are getting unevenness or more surface roughness. So that leads to uh, reduce the quality of the component generated through milling process. So my success rate is very, very low. Then I can to go for another process is also available in additive manufacturing. Okay, so I take the powders of ceramic material, then I can melt using the laser power source, then I can able to print this component without much difficulty. The surface finish which you are getting through additive manufacturing process is much better than CNC machine process. So the problem is solved. My job is very simple in case of ceramic material. In the case of additive manufacturing process compared to CNC machining process. Yeah. So with respect to ceramic or hard materials or brittle materials, definitely you can go for additive manufacturing process. So in the same way, another example, you take aluminum alloy. I have two process, CNC as well as additive manufacturing process. So, so definitely as an engineer, we can say immediately go for CNC rather than AM process. Why? So AM and the CNC also both are competitive to produce the component. The material is aluminum alloy, but the problem is the time consuming in the case of additive manufacturing process much higher than CNC. So the product delivery time is more in the case of additive manufacturing process can be used to develop the component using aluminum alloys. So you can choose depending upon the type of material, type of complexity, then either you can choose CNC or AM process. Then similarly, if you go for complex nature, suppose latest trend is micro channels. So the micro channels are produced in the computer peripherals as well as other defense aerospace applications to increase the heat transfer rate. Then how do you generate the micro channels? And the channel may not be straight. There should be some irregularity. To increase the heat transfer rate, I can go for more complex micro channels, nature of micro channels. So in such a cases, in conventional machining process, I cannot say may not be suitable, may be suitable, but it takes a lot of time and also the accuracy which you are generating through this uh, component through machining process is very difficult. So the additive manufacturing is very simple. Even internal microchannels or external microchannels, it doesn't matter. Only you are seeing that you can generate this model in the CAD environment. That is only the difficulty you can arise in additive manufacturing class. So with respect to complexity nature, definitely irrespective of any material, straight away you go to additive manufacturing process. Yeah. So coming to accuracy as of now compared to CNC and additive manufacturing process will give less accuracy compared to CNC process because, so I'm trying to tell you the difficulties and also the possibilities to work in these directions. So indirectly, I am giving an idea to work on these areas to do your PhD works. So you are developing the model in a CAD environment, then you can convert into STL file. So due to conversion of STL file, some portion may be eliminated. For example, I'm giving an example. I want to find the area of circle using finite element method. So I know the area of triangle, but I don't know the area of circle. For that purpose, I can divide the entire circle into number of triangles. By dividing these, some portion, curved portion is we are missing. So the summation of all triangular areas may not be equal to the actual area of circle. So it is approximated to area of the circle. So similar way, you are converting your CAD to STL file. There is some geometry is missing. So that geometry, whatever the missing, you may not get because after STL file, you are just printing the material in the same as STL file only. So whatever missing before, after the conversion from CAD file to STL file, so there is no chance to getting in future also. So in that case, definitely you are losing some accuracy level. Accuracy with respect to geometry I'm talking about. So one can work on topology optimization. In NIT, some students are working in design faculty. Topology optimization. So once you are doing topology optimization, at least your accuracy level is increasing before applying the topology optimization. So in this way, you can also work topology optimization and you can take the data, you can convert into STL file, then you can print, you can see that without optimization, with optimization, how much accuracy you are going to increase, and how much volume of the material you are going to increase, which is equal to your real one. So I'm combining both the geometry and accuracy. You can also work in these areas also. Then coming to the programming, CNC and additive manufacturing, there is no much difficulty while writing the programming either in CNC or additive manufacturing. Then coming to the last difference is we can call it as CNC 2.5D process, additive manufacturing process, 3D process. Why? Why not CNC call it as 3D process? Yeah, it is not. So in CNC for generating 3D objects, at least you can change minimum one setup. Without that, you cannot able to produce the component. Whereas in additive manufacturing, directly you can produce the component 3D. Then after that, just you can remove the substrate. That is enough. Whereas in CNC, fixing the component in the check or any voice or fixture, so that leads to not getting the geometry in other side. Then again you have to remove this material and I can fix in other portion so that you can generate the geometry in other side. So that side is already which is in the first stage. So that's why we can call it as 2.5D process. Yeah, this chart will give an idea how much time you are going to save using the additive manufacturing process. So because you are generating the CAD file, whatever the CAD file, depending upon the customer demands, you need to just change the CAD file or any dimensions you are going to change as per the requirement of the customer. So that itself doesn't take much time to convert this older one to newer one. That saves a lot of time. Whereas in conventional, you can change the entire process. So that leads increase the time and sometimes you can wait for the final version of the component for a longer period also. Yeah, so this chart will give an idea of what is the production, what is the quantity you are going to produce through additive manufacturing process. Then what is the volume of the material you are going to generate through additive manufacturing process. So somebody says, I want to generate mass production, that is of components through additive manufacturing process. So if you say this word, the people laugh at you. So we cannot use for mass production process. Then what is the size of the part you can generate? What is the production duration? What is surface finish? What are the tolerances? What are the feature size? And based on that, what is the important property, strength and stiffness? Yeah. So we are more working on improve the mechanical properties of additive manufacturing components, either laser-based or non-beam based manufacturing methods. How to improve the strength of the component? For example, you take the cast component and you take the additive manufacturing components of the same material. Those so materials will not give the same property. Additive manufacturing component will give more strength, whereas cast component will give less strength, whereas yield strength cast component is much higher than additive manufacturing components. Right. So this is only the key point to take your PhD also. So what are the problems encountered during additive manufacturing process to reduce the yield strength? Because in design aspects, we are looking for yield strength, not uh, that is ultimate tensile strength. So how much you are increasing the heat yield strength, so that will give you increase the efficiency of the process. That means you can reduce the weight of the entire structure. For aerospace and defense application, this is very important property required for uh, materials which are used in these applications. How to improve the yield strength? What are the problems? Why yield strength is low compared to cast components? Then similarly stiffness, hardness. Then based on that you have choose the selection feasible machines. Then different orientations. Yeah, one of my student is also working on, you can produce the components using different orientations. For example, horizontal, vertical, or mixed horizontal, vertical, or some hatch patterns also people are working. So different hatch patterns, for example, square, hexagonal, and honeycomb structures. So these structures will give an additional properties like strength and stiffness. So depending upon the orientation, the properties also going to change. And what is the spacing between the two layers? How much spacing can be given? Then what is the time you are going to utilize the machine to produce your component? Then how much cost is involved? Then your cost of the component by produced by additive manufacturing is higher than other manufacturing methods. Nobody going to buy your components because first, finally customer wants lower cost at the same time quality. So he doesn't want to look for which process you are produced by this product. He don't bother about. He bother about only quality as well as performance, and also at the same time cost also sometimes. Yeah, if you look at this chart, then you can give a clear idea when do we use additive manufacturing process, when we cannot. So for example, you take a fusion deposition modeling or laser sintering or stereolithography, all are horizontal lines. So this is a conventional injection molding process. You are getting the graph with respect to the cost versus number of components produced in a particular period. So this, as the number of components increases, the cost per unit product is less. So wherever the intersection point, yes, you can focus on these points. For example, you take the stereolithography as a process and injection molding this process. These two processes generate the same components. So the volume of the component is, let us say, 4,000, 5,200. Okay. So if it is 5,200, more than 5,200, your injection molding is a better solution than stereolithography. So if it is less than 5,200, this is much better than your injection molding because the cost per unit is more in case of injection molding compared to stereolithography. So depending upon the quality or type of material you are going to develop the component, then you can choose the process accordingly. So these are the various different applications. I don't want much time on this. So you can find, just you can go to Google search, you can find plenty of applications are available with respect to additive manufacturing process. Yeah, this is defense and aerospace applications using additive manufacturing facility. Then this is the components which we are generating through additive manufacturing process. Yeah, coming to the topic which we are more focused on, uh, friction state additive manufacturing, additive friction deposition, and ultrasonic additive manufacturing, and wire arc additive manufacturing process. So based on the our convenience or easy to understand the additive manufacturing facility, uh, we are dividing these additive manufacturing facility into two groups majorly. One is beam-based additive manufacturing, other one is non-beam-based additive manufacturing process. So the beam-based additive manufacturing process, you are using either laser as a heat source or electron beam as a heat source or any other power source. For example, in welding, you can use arc as a power source. So that arc or laser or electron beam is used for melting the material. So once you are melting, then you can deposit the liquid material in a different fashion with the help of your XY plotter, which is connected to your AM machine, and it will control by AM machine itself. So through that, you are depositing as per 2D geometry. Then after depositing layer by layer, then it is during solidification, it becomes a solid one. So there, the melting of the material takes place. Yeah. When you're talking about melting of the material, yes, you can, I can give an information if you want to learn about more in specialized in additive manufacturing. You can also specialize in metallurgy, also specialized in manufacturing, also specialized in CAD and other areas. So it is not a single hand we can get the useful product which are useful for the nation. It's not. It is a combination of efforts and multiple or interdisciplinary, we can say, together to work to leads to a better solution for the industrial applications. So with respect to the metallurgy and mechanical, and you can have a certain knowledge in metallurgy aspects only. Yeah, when you are talking about beam-based additive manufacturing, you are melting the material. If you are melting the material, what is happening? There is a more chance of gas absorption. So once the gas are inside in the liquid metal, then you are pouring into their certain features or dye, then allowed to solidify, the gas bubbles which are inside act as a porosity. So that leads to brittle failure of the components. This is one issue which we come across even in metal additive manufacturing process. So in that case, you are need to protect from the environments. Then you can choose helium or argon as a gases which are responsible for not to react with the environment. So your problem is solved because of these gases used during additive manufacturing process. There is no chance of oxidation. This is one problem. Another problem is while you are melting. For example, I am showing one of the example, copper and tantalum. I want to add these two materials. Copper is melting point temperature is 1060 and tantalum is much higher than copper, almost 3 to 4 times the copper melting point temperature. So because of the difference in melting point temperature, there is a chances of incompatibility between these two materials. And also thermal conductivity also very important roles. So this leads to cracking of the interface. So once the crack is developed interface, there is no useful product the product is going to waste. But we need application where these kind of two materials are used. Then what is the alternative solutions? The alternative method is non-beam based additive manufacturing process. So just I'm using the new terms that becomes a new flavor to the existing technology. So it is old technology, that is solid state welding. When you are looking for solid state welding, the first most important or very useful process to the world, that is forge welding. So forge welding is a solid state welding. Just you can heat the material to its recrystallization temperature, then you can apply the force. That force is enough to create a bond between the two materials because of the interaction between the atoms. The famous example is iron pillar, which is located in Delhi. Is it is a forged welded components. So it is a combination of several components. Not it is not a single component. These components welded by forged welding process. So with that principle, we can use it in additive manufacturing process. Then you can develop the components. So that is non-beam. So we can use the beam, but that whatever the energy we are using in this process, it will not reach to its melting point temperature. That is our objective. So whatever the energy you are utilizing for only up to recrystallization temperature of the material. What is the importance of recrystallization temperature? Yes. So once you have heated the material to its recrystallization temperature, the grain boundaries are weakened. The strength of the material is the function of bonding between the two grains. So you are applying the heat to destroy the bond between the two grains. So that means the force of attraction between the grains reducing by increasing the pattern temperature. Then you can apply the force according to the force direction, the material is going to deform. So this is my basic principle involved in forge welding. The same principle I can apply here to weld certain components through additive manufacturing process. So those process we can comes under friction stir additive manufacturing, additive friction deposition. So this is originally we are working on friction stir welding and friction stir processing. In the friction stir welding, you are joining the similar or dissimilar materials with the help of the friction. The friction is developed between the tool and the workpiece. The tool is rotated with certain RPM and workpiece is stationary. So due to the friction, heat is generated. That heat is utilized to softening the material and leads to joining of these two materials. Then, so both these friction stir additive and additive manufacturing, additive friction deposition are intensive process that involves severe plastic deformation. So friction stir welding is comes under solid state welding as well as severe plastic deformation takes place. So whenever material undergone severe plastic deformation, it reduces the grain size. The grain size becomes very, very finer when the material undergone severe plastic deformation. So what is the advantage you are getting when the grains becomes finer? Yes. Again, back to your metallurgy. Your yield strength is directly proportional to 1 by square root of grain diameter. So with the help of this technology, I am reducing the grain size that will help you in increasing the yield strength of the same material. So this was done in our laboratory. So we are increasing the yield strength by almost 1.5 times the original material. So that leads to reduce the loss of weight of the entire structure. That leads to increase the efficiency of the process. If a material is used for aircraft or defense applications, you are saving a lot of fuel and efficiency also increased. Yeah. However, there are significant differences, only small differences between these two processes, friction stir additive manufacturing and additive friction deposition. So whereas the other is purely additive process that deposits new track with each pass, with each individual layer undergoing the same type of severe plastic deformation during deposition, reheating afterwards. So one is sheet lamination, that is friction stir additive manufacturing is comes under sheet lamination process, whereas friction deposition is comes under deposition of layer by layer. So when you are looking at the comparison between the three solid state process, ultrasonic additive manufacturing, friction stir additive manufacturing, additive friction deposition. So this is for classification, sheet lamination. The sheet thickness is the order of zero point 0.1 mm, whereas sheet thickness is in case of 1.5, there is no, because you are adding the material, there is no sheets here. So hybrid process, both are possible. We can use hybrid technology. I'll tell you how to, why hybrid process. Then coming to the additive friction process, we cannot only single process. The resolution limiting factor, subtractive process, here also subtractive, here tool geometry is a very important role. The temperature and microstructure similar to pre-processed. This is also very important. Some materials, suppose for example, if you use strain gauges, so your strain gauges are embedded into the material. So once you are embedded through this ultrasonic additive manufacturing or fiber optics, so the properties doesn't change even after the process also. So that's why this process is very useful for such applications. Initial and after process also behaves the same material property, whereas in other two cases it's not. It may increase or it may decrease depending upon the condition of the process parameters, whereas in this case it is not. Yeah. Now I'll go to this friction stir additive manufacturing. Yeah. So as I said, this is friction stir welding process. So this is the tool. Just you can see the tool having a shoulder as well as a pin, and there are different layers: layer one, layer two, layer three, layer four. Just you can add these. Just you can rotate the shoulder, and also you can apply the downward force. Due to that, just the bottom pin is portion of the pin is contact the top surface layer. You can rotate because of the rotation, there is a friction develops between the sheets, that is a layer 4 top of the layer 4 sheets and the bottom portion of the pin. So that leads to increase the heat generation. So that utilized heat is transferred to the below the layers, and you can apply the downward force, it automatically pierce into that. So once it is pierced up to the shoulder contact, so this is the bottom shoulder. Once it is contact with the top surface of the layer 4, then again it is still rotating, then lot of friction also develop. So that friction is transferred to the other materials. So once it is rotated and also once it reaches to requested temperature, then you can give movement to the tool in the direction of the process. So once tool is rotated anti-clockwise and moving in the direction, the metal is moved from the advanced to rotating side and settled at the back side of the pin. So once it is done onto these four layers, just you can talking about this portion. So this portion initially these four layers are separate. Then after processing, these four layers are bonded together to become one unit. So the layers may be similar material, may not be similar material. So depending upon the applications, you can choose different materials. Suppose if I use the component layer 4 and layer 1 is harder material, layer 3 and layer 2 is softer materials, having a more or less same melting point temperature, I can use it for certain applications. For example, you can take shoe brake. The outer layer and inner layer should be stronger than 2 and 3 because when 2 and 3 is soft nature, whatever the vibration that are coming when you are applying the brake, that vibrations transfer to the 2 and 3. So because of this soft nature, it will have more absorbing capacity of the material, of the material. So that leads to improve the life of the component. So this we can call it as a functionally graded materials. So functionally graded materials, the properties are going to vary along the particular direction. So the 4 and 5 is much harder, that is hardness is much higher than 2 and 3. So in this way, we are going to develop a component through friction stir additive manufacturing process. So in this process, I'm not heating the material to its melting point temperature. Just I am heating the material which is required to recrystallization temperature only. So once you are optimize the process parameter, you can get a better joint or better additive manufacturing process. Now you may get it out. Suppose I want to have entire component of additive manufacturing, only not only this portion. We can also do. We have done our students. So you can also do the same process again and again so that you can build the entire additive manufacturing components. So this is one area you can work in your, your research work. So here the tool is much higher, harder than the material which you are going to process it. So for example, if you are working on aluminum alloys, the tool metal is H13 tool steel or steel based tools is enough. So here the downward force is an action to create a bond between these two materials and also will help you to increase the heat generation. The rotation of the tool will give the movement of the material from one side to the other side and fill the back side of the pin. So in this way, you are going to generate the components. So just I am showing one video related to hybrid welding process, hybrid additive manufacturing process. So additional tool is added to here, that is the removal of unwanted material from the processed component. So that you can save the setup time. Yeah, these are the two components. Initially, there are different materials, different layers. Now, after processing, you can get the final component. So, in this way, we can produce either similar materials or different materials of same material with the different hardness also can be possible. Yeah. Then coming to another process, additive friction state deposition. So what is this process? How we are going to develop this component? So here, that same tool, before going to this, just I'm doing comparison between the two process. So using this principle, we are developed the component in the earlier video. So here, shoulder and the pin, there are pack of sheets. Then just you can process it so that this final component becomes the additive manufacturing components. Whereas in this case, you have a hollow shoulder instead of solid one. So in the hollow shoulder, you have a material which is going to deposit onto the substrate. So this metal is very low melting point temperature compared to the shoulder, hollow shoulder material. So once you are rotating the hollow shoulder, then the friction generated between the bottom of the shoulder and the substrate initially. So that heat is, because of the friction, heat is generated. That heat is transferred to both the substrate as well as the inside material, which is kept in the hollow shoulder. So because it is low melting point temperature, it reaches to initially recrystallization temperature, then you can apply the anyhow, you can apply the force. Due to the force, it is just deposited onto the substrate. So that is the difference between additive friction deposition. So here, one of the filler material is in the form of a rod, which can be made through any other manufacturing process, normally drawing process. Then you can able to get this type of rods that inserted into the hollow shoulder. Then you can use the same principle to deposit the substrate. Yeah, in the schematic way, this is a yellow color is the filler material, either either in the form of powder or rod form. Rod form is very easier than powder form. The powder form is very difficult to produce the powders without any defects, whereas rods can be used without any defects. So you can produce these components in this fashion. Yeah. So what is the advantages using this additive friction stir manufacturing process? You can see the accuracy as well as building rate. So this is powder-based fusion process, a direct energy deposit process. These two processes are beam-based additive manufacturing process. Now we are talking about green color, that is additive friction deposition. So you have wide scope or wide spectrum with respect to the accuracy as well as the building rate. The building rate is much higher than the powder-based additive manufacturing process. But every process has its own advantage and limitations. For miniature components, you can go for powder-bed fusion process. For large sized components, you can go for additive friction stir manufacturing process. Yeah, this is another techniques which we generate uh, functionally graded materials using the knowledge of additive friction stir deposition process. So this is one of my research student work. So our aim is to generate functionally graded materials through this technology, that is additive frictions deposition. How we are going to generate the simple techniques. So initially we take the bulk material, just you can make a groove, then we can fix we can take the tool and consist of a shoulder as well a pin. The length of the pin is slightly lower than the length of the groove, thickness of the groove. So once you have filled the reinforcement particle into that, just you can do the process it. Once the process is completed, then you are getting the red color of your matrix and reinforcement. Then what we do is next step is again you have to make a groove on this. Then you can fill up again powder particles. Then you can do the process again. So once you are coming to third stage, you are getting the different volume percentage. So initially red color is the lower one and the green color is slightly higher than the red color one. Again, you can apply the same procedure, making the groove and fill the powder and do the process. Then finally, you are going to get this kind of variation of volume percentage of the reinforcement particles along the thickness direction. So this is an example of a shoe break again. So you want to have more hardness at the outer layer, which is always contact with the rim of the wheel. So this blue color layer will be much harder than the green color one. In below one, you are getting the low volume percentage compared to the blue one. So that leads to improve the in vibration, absorbing the vibration from the system. So once you have developed this component, then you can analyze the microstructure and also you can do another characterization techniques. So for developing the functional grade materials, you are using different pin lengths, not the same length of the pin. So different pin lengths can be used. Then you can see the microstructure of the processed region. The bottom region, SiC, silicon carbide, is a reinforcement material. That lower region and SiC rich region is in the top region, and the middle region you have a moderate region. So there is some variation of the reinforcement particle from the top to bottom. And also you can characterize by taking the phase volume fraction of the microstructure, the top region, bottom region, and below region, lower region. Just you can see the observation, the 14%, 14.03 plus or minus zero point 0.3, and there should be variation in three samples. Then second region also, there is a variation in the three samples. Then third region also. Just you can observe the one sample, here 14%, here 11%, here 9%. So there is a variation of SiC because we are added like that, so that the same observation we can found in microstructure. Then you can see the your hardness values from the top to bottom. So this is the top region, this is the bottom region. The hardness also going to increase from the top to bottom. So this top region having higher hardness because rich content of silicon carbide, that's why it has higher hardness than lower one. So because of this, the variation of the volume percentage increase leads to variation in the hardness. So that help in our applications like a shoe brake and other landing gears, etc. of aerospace applications. So underlying material science, additive friction deposition is a thermomechanical process. Important process parameters include rotation of the shoulder, shoulder normal force, filler material, feed rate, and layer height and transfer speed, etc. The microstructure formation and applicability to non-weldable alloys is the same in both friction stir welding and processing. A shoulder with a protruding pin is spun at a higher rate and inserted into the softened material space. The shoulder then traverses the material to either join or to interfaces in friction stir welding or treat the surface in friction stir processing. Yeah, in friction stir welding and processing, the stir material is surrounded and constrained by the material in the form of in the thermomechanical effector zone into which heat is transferred by thermal conduction. The feature capabilities, the peak temperature of an additive friction deposition process normal ranges from 60 to 90% of the melting point temperature. So because of the absence of melting, as I said earlier, parts do not suffer from the issue associated with the rapid solidification, porosity, hard cracking, elemental segregation and dilution, aggregation of finally dispersed oxide particle and residual stresses. The low porosity and residual stresses in the as deposited part render post-processing heat treatment unnecessary, although post-processing surface finish is often required. Yeah, these are the just you can see the applications as I mentioned in the previous slides. The copper and tantalum, the copper and niobium. So images of bent test for tantalum and niobium coating deposited on a copper substrate, which showing the strong mechanical bond and no delamination under bending. So there is no delamination between these two layers. So successfully deposited friction stir ready to deposition process using this uh, technology for even though materials are different uh, different melting point temperature, even then you are getting without much difficulty. The flexibility in feed material, based process have restriction of feed material in terms of powder compaction, shape and size. So these impose a greater barrier for widespread implementation. Metal AM in contrast, additive friction deposition can use solid rod from cast or wrought alloys as the feed material. So sometimes you can also feed material as a powder form or rod form depending upon your requirement, depending upon the process. Yes, you can go ahead. So this is one example of large window frame made up of 6061 alloy, which is used in aerospace applications. Use making the using this technology friction stir additive manufacturing process. So this chart will give an idea of non-beam based and flexible bead material, scalable, no melting point temperature, low energy, low cost, and cast alloys, consolidated powders, etc. Then dynamic recalculation, no certification. Then if you are dynamic recalculation, as I said, refinement of grain size takes place, and also you can get equiaxed grains and isotropic properties. So with this, you can able to get better yield strength than the original materials. Here, no solidification because no melting at all. So leads to low porosity, low residual stresses, no hard cracking, low elemental segregation, no aggregation of oxide particle, no non-weldable materials also possible. So apart from the advantages, there are certain limitations. So the limitations, the development of additive friction deposition based technology has focused on increasing the part size and build rate. As a result, the shoulder and the filter dimensions are large, leading to large in-plane feature size. While powder bed fusion can make parts with a small feature size on the order of 0.5 mm, the in-plane resolution of additive friction deposits is limited to approximately 10 mm or above region given the current tooling capability. Yeah, there is latest technology in additive friction deposition. The deposition path is guided by G-code based hash pattern. Since algorithms are available to automatically convert your CAD file to G-code, it is straightforward to go from CAD file to the part long as the geometry is printable. Yeah, so you can also interface your CAD file to the additive manufacturing facility, the friction set additive manufacturing. So whatever the data is available in the CAD file, that will convert into G code. There are softwares are available to convert your CAD file to G code. That G code can understand by your machine. Then you can able to print the components as equal to your CAD file. The printable geometry is limited by the in-plane resolution and maximum overhang angle in additive friction deposition. Given the layer by layer nature of additive friction deposition, parts may require additional post-processing required sometimes. The another issue is which is concerned with the friction stir deposition or additive friction deposition. The buckling is the main issue because you are increasing this after certain height, then because your need to apply downward force is a compulsory. So without that, you cannot able to get proper joints. That's why after building certain height, there is a problem with the buckling. So it is restricted to certain height only. It depends upon the material, the height decided by the properties of the material which are going to build through this process. And tooling shoulder life is also utmost concern because continuous rubbing action takes place between the uh, substrate and or deposited material. So that is reduce the life of the tool. Then you need to work on increase the tool life by adding different treatments or different alloying elements to increase the wear and resistance. Yeah, with this I can conclude my lecture. Then we can discuss more on uh, doubts and or any other clarifications uh, before going to yeah. So this is ultrasonic. Just you can see the applications of ultrasonic fiber embedments through this process. Very easy to embedment. Then there is no change in the properties of the fiber particles, etc. Yeah. Smart structures also you can develop through this process. Smart materials, smart structures, then sensors can be placed in the materials. Some defects because of the unevenness of the materials and also lack of fusion that leads to defects in the properties. Yeah, yeah. With this, I can stop my lecture. Then it is open for discussion. If you have any queries, I can clarify within 10 minutes.
Thank you, sir. Thank you for this insightful lecture on additive friction stir deposition. So I'd really like to thank for enlightening us. From participants, if anybody is having any query, so you may unmute yourself and speak. Anyone from the participants, please unmute yourself and you can discuss if you have any query to the related topic.
Otherwise, you can also post in the chat box. Your question, you can post in the chat box.
Yeah. Srivastava?
Yes, sir.
Yeah. Thank you, Kumar sir, for your wonderful lecture today. I think it's very useful for upcoming researchers and for faculty. Really, once again, I thank you because you are always part of the department and program. Whenever we require your support, you are always be kind enough to solve the issues in the department. Really, on behalf of that, really, and thanks you really. Maybe the people are going to start their research in the this is a new area, and people may think about it, I think.
Yeah.
So the future, definitely, there is a huge scope is there for this topic really. Thank you, Kumar sir.
Yeah. Thank you very much. Thank you very much for the department as well as the institute as well as the head mechanical engineering as well as coordinators for giving me this opportunity to share my knowledge in the FDP program. Thank you, one and all.
Thank you,
Thank
sir.
you, sir.
So I can leave the meeting with the
Yes, sir.
permission. If there are no queries, let's leave the meeting.
Okay, till now no queries came, sir.
Okay. Okay. Thank you. Thank you once again.
Okay,
Bye.
sir.
Thank you.
Welcome. Srivastava,
Sir.
so we can announce for the next session.
Yeah, there is a little bit change in our next session because the speaker for the second session is Professor Janki Ram sir from IIT Hyderabad. So suddenly some important interview came in his department. So on his request, we have shifted that second session after the third session. Means it will start at 4 o'clock. Am I correct, sir? Pankaj sir?
Yes.
Yeah.
Just after 4 o'clock, it will start.
Yeah, so now we don't have our second session as per our regular schedule. Our third session will start at 2:30 p.m. and it will end at 4 o'clock. At 4 o'clock, the lecture will be given by Professor Jankiram, and thereafter we will be having our this validatory session.
And followed by the test.
Yeah. So we request you all to join the session at 2:30 p.m. and
And that will
for
be the live session which will be taken by Professor Sriram Venkatesh, and he will give about the what are different additive manufacturing systems are there, machines are there. He will give the demo on that FDM machine and the metal 3D printing, all and the scanners. What are the scanners that are used for the scanning of the object and for rapid prototyping. So I will go to share the
feedback link, sir. Feedback link.
feedback link. Yes. So feedback link just posted in the chat box. All of you fill this Google form, and I'm also going to send sharing. So shall we close now?
Yeah.
Okay. So again, we will meet at 2:30 sharply. So thank you, everyone.